Hi you guys, I'm back with another projectile motion problem. If you want to be stronger than you were at the start of the video, pause at some point and try to make progress on your own. And if you don't, then try again later. Okay, with that said, let's get started. So, a man stands on the roof of a 15-meter tall building and throws a rock with a velocity of magnitude 30 meters per second at an angle of 33 degrees above the horizontal. You can ignore air resistance. Calculate A, the maximum height above the roof reached by the rock. B, the magnitude of the velocity of the rock just before it strikes the ground. And C, the horizontal range from the base of the building to the point where the rock strikes the ground. And D, draw a bunch of graphs. Okay. So I'm going to draw a picture to visualize this. So we have a building here. A building here that's 15 meters high. And so it's unfortunate that I think the problem here is poorly worded. If they say that the man throws the rock, then they should give us the man's height so that we can add it to the building's height, but they don't. So I think it's more appropriate to say that he kicks the rock from the ground of the roof. So I'm going to choose my origin to be at the bottom of the building. The vertical axis, as always, is the y-axis. That's should be straighter, but yeah, the horizontal axis is going to be x as usual. All right, so we want to calculate the maximum height above the roof reached by the rock. So it's very important to note here that the question is asking for the maximum height above the roof. So the trajectory of the rock is going to look something like this. The question is not asking for this distance, which is y max. No. What the question wants is this distance, the height above the roof. So this is going to be delta y. So it's the maximum height minus the height of the building, which is 15. So let's consider the motion in the vertical direction. Let me use a different color. So I'm going to say part A. So vertical, kinematic equation for that is going to be y equals y naught plus v0yt plus 1/2 ayt squared. Now, when I say delta y, what I mean is the maximum height minus this initial height. So that's going to be y minus y0 in this equation. So I'm going to subtract both sides by y naught. So y minus y naught equals v0yt plus 1/2 ayt squared. So this quantity here is going to be delta y. That's what we want to know. Okay, so we need the v0y. That's the component of the initial velocity along the y-axis. So I'm going to draw a triangle. So the rock is kicked like this. This is the initial velocity vector. I'm going to draw the triangle with the vector's magnitudes. So the hypotenuse is v naught. That's going to be the 30 meters per second. Its the component along the y-axis is going to be v0y. That's what we want to put right here. And the component along the x-axis is v0x. We don't really care about that because we're considering only the vertical motion here. Oh, and the angle. Angle is 33 degrees above the horizontal, so that's going to be this right here. So to relate v0y with the angle and the hypotenuse, I'm going to take the sine of 33 degrees. That is the ratio of the opposite side, which is v0y, over the hypotenuse, which is v naught, which is 30 meters per second. This is v0y. And now if I solve this for v0y, I get 30 times sine 33 degrees. So 33 degrees is not one of the standard angles, so we're going to have to use a calculator to figure out what this is, which is okay. I'll just leave it as sine 33 degrees for now, because it's very likely a long decimal. So delta y equals 30 sine 33 degrees times t. All right, so ay, that is the component of the rock's acceleration in the y direction. So the only force acting on this rock as it moves through the air is gravity, which is completely vertical. It's gravity points downward always. Let me use a different color. Gravity points downward always, and that's in the direction opposite. It's in the it's pointing downwards, and I chose my positive y to point upwards. So ay is going to be negative g. G is the standard acceleration due to gravity, 9.81 meters per square second. Oh, whoop. Minus 1/2 gt squared. So we don't know what the time is. Time t is the amount of time it takes for the rock to go from its initial position to a final position. I'm choosing that final position for part A to be at the very top at the very top. So the time to go from the top of from the roof of the building to its maximum height t. That's what t represents here. We don't know what t is, so we need another equation to figure it out. So I'm going to use the kinematic equation for velocity now. This one is the kinematic equation for position. So the one for velocity is Vy equals V0y plus AYT. The vertical velocity at the top of the motion is 0. It comes to a complete standstill at the very top of the parabola. So Vy is going to be 0. V0y is what we calculated here, which is 30 sine 33 degrees. Ay, that's going to be negative g, so minus gt. And we have here an equation with only one unknown, t. We can solve for that. So I'm going to bring gt to the left side. So gt equals 30 sine 33 degrees. And if I divide both sides by g, I get t. 30 sine 33 degrees over g, which is 9.81. Again, this is the time to go from here to here. All right, so let's get out the calculator. 30. All right, so this only accepts angles in radians, so I'm going to multiply this by pi over 180 over 9.81. That's what t is. So it takes 1.67 seconds roughly. 1.67 seconds to go from the roof of the building to the top of the motion. And I'm going to plug this this value for time into the equation for delta y, which is going to be our answer for part A. That's this here. 30 sine 33, and then multiplied by t, which is the 1.67 seconds, minus 1/2, 9.81, and then times the 1.67 squared. 13.6 meters above the roof. So this is our answer for part A. All right, let's see what's next. Part B, the magnitude of the velocity of the rock just before it strikes the ground. Okay. So the final velocity vector is going to look something like this. It's going to have a, I'm going to call it V. So we're doing part B now. It has a horizontal component, Vx, and it has a vertical component, Vy. Now, this Vy that I'm talking about is different from the Vy in the previous part. In the previous part, my final position was the top of the parabola, but now in part B, my final position is right above the ground, so it's going to be right here. This is my final position now in part B. So the Vy I'm talking about is not Vy here. So the magnitude, okay, so what is Vx? So because there's no air resistance, the horizontal component of velocity does not change. It's going to be V0x here and here. So Vx equals V0x. Oh, whoops. That's a subscript. And from this triangle here, from the initial velocity vector, cosine, I take the cosine of 33 to get V0x. So cosine 33 degrees equals V0x over 30 meters per second. That's the magnitude of the initial velocity vector. So V0x is going to be 30 cosine 33 degrees. Now, what is Vy? So we use the same equation as in part A. Vy equals V0y plus AYT. V0y, that is going to be the 30 sine 33. Right here. AY, that's going to be negative g. And t. T now is the time to go from the top of the roof to the floor right here. We don't know what t is. We need another equation. So I'm going to consider the vertical motion again. So it's going to be y equals y naught plus v0y t plus 1/2 ay t squared. So the final position y is going to be 0 because it's on the floor. Y naught, that's where it starts out at. So 15 v0y is going to be 30 sine 33. T, and then ay is negative g, so minus 1/2 gt squared. So we can solve. So even though it's complicated, it's a quadratic equation. We can solve this for t using the quadratic formula. I'm going to multiply both sides by negative 2. So I'm going to have it so that 0 is on the right side. So I have gt squared minus 60 sine 33 t minus 30 equals 0. So if I use the quadratic formula to get t equals 60 sine 33 squared plus or minus square root of 60 sine 33 degrees squared minus 4 times negative 30 times g. And all of this is over 2g. Whew, okay, so that's going to be a mouthful to put into this calculator here. So 60 sine this is squared, and then so now the question is, do we use the plus sign or the minus sign? Let's evaluate both and see what we get. Oh, I'm sorry, this is, whoops, this is not squared. This, however, is squared. Get rid of that. Okay. Minus 4, negative 30 times 9.81, all over 2 times 9.81. So that's 4.08 seconds. That's one time. And now for the minus sign, what do we get here? Okay, so negative 0.749. 0.749. So because this is negative, we can automatically discard it because we assume that that the rock at this point is at t equals 0, so it should be at a positive time when it hits the ground. So we can easily dismiss the negative value of t. So we're going to use the positive value, which is 4.08 seconds. And now that we know t, we can plug it into this formula here for Vy. That is the vertical component of the final velocity right before it hits the ground. So Vy, approximately 30 sine 33 degrees minus g times 4.08. Let's get out the calculator once more. Copy, paste. Thirty sine 33 over 180 times pi. And now minus 9.81 times t. Negative 23.7. meters per second. Let's see, the question is asking for magnitude of the velocity, so we don't care about the angle. We just want the the magnitude of the final velocity vector is going to be v squared equals vx squared plus vy squared. So that's going to be, so v is square root of (30 cosine 33 degrees) and plus this negative 23.7 and this will be our answer for part B. So I'm going to copy and paste all of this. This is Vy. So square root squared plus. So this here is going to be 30 cosine 34.6. That is our answer for part B. Let's have a peek at the final answer, and I mean at the answer at the back of the book, and see if we are okay. Wait, which problem is this? This is 3.21. 34.6, I believe that's what we have. Yep, so we're all set. Okay, part C. Horizontal range from the base of the building to the point where the rock strikes the ground. Okay, so we've considered vertical motion so far. Now we need to look at the horizontal motion. So this is going to be x equals x naught plus v0x t plus 1/2 ax t squared. X is what we're looking for. That's the final position. So this here's the final position, and this here is the initial position x naught, which is 0. X equals 0, and v0x, that's 30 cosine 33 degrees times t, and ax is 0 because there's no air resistance. T was this 4.08, so we can plug that in to the calculator. This here is our t, and 30 cosine 33 over 180 pi (103) meters. That is our range. Final answer. Yes, it is. Nice. What else do they want? Draw xt, yt, vxt, and vyt graphs for the motion. Okay. All right, so that's this here is our equation for x. So x equals 30 cosine 33 degrees times t. The graph of xt is going to be a straight line that goes through the origin with positive slope, like this. The slope is 30 cosine 33 degrees. And it goes up to 4.08 seconds, because once it hits the ground, it doesn't just keep going indefinitely to the rock does not keep going indefinitely to the right. Once it hits the ground, it stops. So after 4.08 seconds, it's just it just stays at the 103 meters. So this here is the graph of x versus t. Now the graph of y versus t. So it's going to be this equation here. So y initially is going to be 15, and then plus 30 sine 33 degrees, t minus 1/2 gt squared. So this here is is a quadratic equation in t, so it's going to be in the shape of a parabola. It's basically what we drew here in the visualization here. It's going to be this parabola here, very roughly. You know what? I'll draw it again here just to sketch it. But so this here, vertical axis is y versus t. So it's going to stop at 4.08. The height is going to be at 0. So it starts at 15, and it goes like, goes like this. It should be parabolic, but we can use the plot function. So 15 plus 30 t, and then minus 1/2 9.81 times t squared. T goes from 0 to 4.08. And yeah, that's pretty much what we drew here. But it's much nicer than the sketch I drew. Um, but yeah, that's basically the idea for that. So x versus t, y versus t. What's next? Vxt and vyt. Okay. Where are these equations? Right, so this here is going to be our formula for Vy. It's going to be 30 sine 33 degrees minus gt. So it's linear in t, so it's just going to be a straight line with that has a negative slope, so it's going to go down because of this negative g here. I'll just draw it right here. So this here is going to be Vy. This here is t. So when t is 0, it has a maximum of 30 sine 33. And then it's going to go down like that. Oh, I see. So t ends up at 4.08. So the maximum value is here, and it's going to go like this and have a final value of negative 23.7 if we draw it all the way down. So when you throw it, it goes up, and then once it reaches the top of the parabola, it has a vertical velocity of 0, and then starts to fall back down. So Vy becomes negative, and it goes faster and faster and faster until it hits the ground at this point here, and then it just stays at 0 forever. So this is our graph of Vy versus t, and finally Vx. Where is it? Ah, here it is. Vx is just a constant. It does not depend on t at all. It's just 30 cosine 33. So the graph looks like a straight line like this. Ah, it's not. I didn't draw it very straight, but versus t Vx. So it's going to be straight like that until it reaches 4.08, and then it stops moving to the right. So once it hits 4.08 seconds, Vx is 0 all the way to the right, like this. And this y value here is 30 cos 33 degrees. Yeah, and those are the 4 graphs. This problem was long, my goodness. Okay, let's go ahead and call it a day there. Thanks very much for watching, and I'll see you for the next problem.